So now let's discuss how to estimate population mean when the population variance is unknown. When we want to do that, then obviously we need to do some adjustments. The main reason is because now we are unable to calculate the standard error. Okay? The standard error depends on sigma, the population variance, population standard deviation. So this quantity is not available to us. In this case, intuitively, we will try to replace sigma by small s, where small s is the sample standard deviation. Suppose we really replace sigma by s, then we can do all the steps with the method we know. For example, in the retail example, we have 7 sample numbers, this 7, okay? And then we will simply do a calculation about my sample standard deviation like this. Don't forget the denominator is 7 minus 1. And then we will get a number which is around 140 as my sample standard deviation. We may then use the sample standard deviation to approximate the standard error and then to construct an interval. The only thing that we need to worry about is that x bar is not a normal distribution like this, right? X bar would be a normal distribution with sigma here, but we don't have sigma, so we use S as a proxy, and unfortunately, X bar would not be this normal distribution. And if we cannot say anything about X bar, about the probability distribution of X bar, we cannot go further. So we need some adjustments, and luckily we have it. Suppose capital S is the sample standard deviation, which is again random before sampling, and the small s is the realization. So very common, we use capital letters to denote random variables and the small letters or lowercase letters to denote the realized value. Then when we replace sigma by capital S, we have some other facts about sampling distribution. Suppose the population is normal, then we have a quantity which depends on x bar, mu, capital S, and small n. This particular quantity will follow the t distribution with degree of freedom n-1. Also, we have several new terms here. We have a t distribution, and we have something called degree of freedom. And also we have a very weird formula. Okay? So let's try to look at it. So first, the first fact is that as long as we complete sampling, we will get x bar and the small s. Okay? Those two numbers will realize. And then we also have small n, right? So then we know what's the formula here. You probably want to ask, but we don't know mu, right? But mu is a constant. Mu is somewhere there. So all the numbers will be fixed. We don't really need to calculate it. The only thing we need is to see that this particular guy will follow a t distribution. What's a t distribution? Somehow it's a distribution. So we know its density function. We know its how its curve look like. But interesting thing is that we don't need to know what's the density function. We even don't need to know how it look like. Even though I will show you. The only thing is that we only need to use software to calculate those relevant probabilities. T distributions have only one parameter, which is the degree of freedom, and which is n-1. Okay. For any probability distribution, there may be some things that controls the shape of the distribution. Like in normal distribution, it's mu and sigma, okay? The mean and standard deviation. For t, the family of t distributions is very simple. You either have a large degree of freedom or a small degree of freedom. Here, the concept of this degree of freedom is somewhat too advanced, so I don't want to explain details. Please, at this moment, just memorize it as n-1. When you have a large sample, then you have a large degree of freedom. When you have a small sample, then you have a small degree of freedom. This n-1 somewhat captures the fact that now you have capital S as in part of your formula for calculating these statistics. Okay? When you have one more unknown variables, when you have one more random outcome, then your degree of freedom is going to be subtracted by 1. Anyway, this is somewhat too advanced, so please just have some concepts in mind. That's good enough. Okay, so I now do not know what's the probability distribution of x bar, but I know the probability distribution of a formula of x bar. That is good enough for us to do estimations. As you will see, what we will do is basically almost the same as what we did with norm variance. It's just that we need to do some tiny adjustments to carry the calculations. In R, the functions we will rely on is PT and QT. Okay, these are just the brothers or sisters of P norm and Q norm. Okay, P norm and Q norm works like that. Given a quantile, what's the tail probability? What's the left tail probability? Or given a left tail probability, what's the quantile to get that? When we are calling P norm or Q norm, we are talking about normal distributions. When we are talking about PT and QT, that's about the T distribution. So indeed, what's the T distribution? Anyway, it's something like this. T distribution is always symmetric, centered at 0, and bell-shaped. Very similar to normal distribution, but it's not. Okay, very similar, but it's not. So that's what we say when the population variance is unknown, we need to do some adjustments. That's to replace the distribution to some other thing that is close to the normal distribution. When n gradually goes up, the T distribution will gradually approaches the standard normal distribution. Okay, it will become steeper and steeper and steeper and become very, very similar to standard normal distribution. T distribution has a very interesting story, which has nothing to do with mathematics. But anyway, T distribution is called the student's T distribution. Okay, student, so it's your distribution, it's not my distribution. No, just kidding. The story is that the author, called William Gossett, this particular person works in a chemistry factory, and that company forbids employees from publishing their findings. So when Gossett really found something about statistical estimations or about T distribution, he wrote a paper to this journal Biometrica about applying biology and statistics to any kinds of chemical or biological production environments. He used the name student as the name for paper author. Okay, so after that publication, this T distribution become quite well known, and then many people call it students T distribution or students distribution. Yeah, that's how we have that name. And even today, we still say, let's do the students T distribution. Oh, that's some interesting story. Anyway, let's go back to mathematics to see how to apply the T distribution. So before sampling, we expect to see X bar and capital S. We want to find a small b so that when we construct an interval, we can calculate its probability of hitting or covering the population mean. Okay? Oh, so everything's the same, except that we now do not know sigma squared. Now, because even though we don't know the distribution of x bar, we know the distribution of this guy. So how may we use this? This is the quantity we want to find. Okay? So we know we may do some organization, and then this is the probability. The probability for us to cover the population mean is the probability for x bar to be close to mu enough. Okay, something we already know. Now, how about this? Let's subtract each term by mu. Okay, then we get these denominators. And then let's divide each term by s over n squared. That's going to be the denominator. From here to here, obviously the probability does not change, right? And then we will get something like this. And then this is exactly capital T, right? So now, once we can get small s, we will be able to calculate the probability. Oh, we do not know sigma squared, but it's fine. As long as we have the sample standard deviation, we may still calculate the probability with this new formula. It's just that now we rely on a different distribution. So for the example we just have, we know the standard sample mean, we know the sample standard deviation. Suppose, for no reason, I propose an interval 860 and 1060. So I'm choosing a leg size 100. Then I'm going to calculate this particular probability. I now plug in numbers. B is 100. S is 140. N is 7. Okay, and then I want to calculate this probability. And then for me to calculate this probability, I first can calculate the left-hand side number and the right-hand side number as 1.887. And then all I need to do is to find the correct T distribution to use and then calculate it. The T distribution is symmetric, right? So again, now I ask, if the mean is at 0, what's the probability from negative 1.887 to 1.887? So once I call this function pt, I'm going to get the left tail probability. Multiplied by 2, I get 2 sides. And then use 1 to minus it, I get something remains. That's my probability for making a correct guess. And in this case, it's around 89%. Don't forget that the last argument for PT is the degree of freedom of your T distribution. Okay, it's always n minus 1. It's always n minus 1. So it's 7 minus 1 in this case. So conclusion is that we are 89.2% confident that the average number of daily consumers lies within 860 and 1060. Given any interval, we may still calculate how confident we are. Obviously, sorry, I shouldn't say that. We can show you that with from known to unknown population variance, this kind of confidence will be expected to become smaller. Okay? Because we have fewer information, our estimation will be somewhat less inaccurate. With the same confidence level, with the same interval length, our confidence will become smaller. Or say it in another way, for a given confidence level, our interval size will be required to be larger, okay, in expectation. But anyway, that's not a big deal. We are still able to find confidence intervals for us to be that confident. That's still something useful. Thank you.